Okay, let's begin. So we have been looking at noise in our op-amps. So in the last class we looked at noise in the 5 transistor OTA. So just to refresh the result, we basically saw here the noise contributed by this input differential pair that directly appears at the input referred noise, because the noise of these transistors are modeled by an equivalent voltage source at the gate, so that directly appears. Whereas for the current mirror transistors, it has a scaling factor. Wherever I wrote it, yeah, it has a scaling factor of GM3 by GM. It has a scaling factor GM3 by GM. Right. Similarly, we also looked at the offset for this 5 transistor OTA, and once again for the offset, the threshold voltage mismatch of the input pair that gets added directly to the input referred offset, and the offset due to the current mirror is again scaled by the same scaling factor. Great. And then we also looked at the telescopic cascade, and here also we noticed that interestingly the noise contributed by the cascade devices, they are 0 as long as the output resistances are ignored. So here also the effective input referred noise is only due to the input devices and the current mirror devices here. Same is the case with offset. Cool. So that is one thing to remember. So cascade is your dear friend. So he'll come silently in your life without making any noise and boost your life, right? So after telescopic cascade, what did we see in the op-amps? Yeah, folded cascade, that is basically extension of telescopic cascade. Let's see if I can draw it quickly. I will not solve it fully because we have already done this telescopic cascade. Folded cascade is an extension. So okay, I'll have to anyways erase this completely. So the difference is here if the NMOS is the main current source, the cascade will be PMOS. So I'll fold this current here and then push it to PMOS cascade. So same here. So this is the cascade, and at the bottom side we also need to have another cascade, that is NMOS. So this here folded cascade. Hopefully it's not new. So here also again, if you look at, of course I need current sources here to bias it, right? So let us say now we have ideal current sources. Right. So for starters, let's assume the current sources are ideal. Then what can you say about the input referred noise here? Which all devices do you think will contribute? So let me label it quickly. M1, M2, let's say it's M3, M4. Or I think, let me follow the same thing I did last time. I think this was M3, M4. So here which all transistors will contribute to input referred noise? Again, ignore or not. M1, M2, that will directly add. M0's current, as we saw in the last class, that gets cancelled. What about M5, M6? It is a cascade device. Again, if I ignore R0, nothing. Same with M7, M8. So M3, M4 will again contribute to noise. And again, with respect to small signals, as you know, there is no difference between this guy and telescopic cascade. The results are same. But this unfortunately will not be an ideal current source. We have to replace with transistors. So if you replace with a PMOS current source like this, maybe I'll draw it a different color. So this is the only additional set of transistors that we add in a folded cascade compared to the telescopic cascade, right? So I'll give it as an exercise. You can work out. You will find that these guys will indeed contribute to noise. Okay, and okay, can you tell me what will be the, if I find the short circuit noise current here, due to M10, what do you think will be the noise contribution? If I call it IN10, let's do that, it's fine. how much of this current will flow to the output? This current is injected into this node. So here, how many paths the current can take? It's again small signal analysis, nothing new. So it can go here to this guy or here. So look at the impedances at each of these points. This direction, what is the impedance? R0 is ignored, that's open. So here, what is the impedance? That is another output resistance that is also open. So what will happen to the current? It will completely flow down and add here. You can argue the same way for this guy also. This current will also completely flow here and gets mirrored here. So these guys will indeed contribute to additional noise current. So that is the price you have to pay for having this folded cascode. So similarly, if you find the offset as well, again the input pairs will contribute to the offset. These two current mirror transistors will also add to the offset, and you will find that the additional current sources, they will also add to the input referred offset. Okay. I'll give it as an exercise, you can work out. So yeah, so that is the price we have to pay. But what is the advantage with folded cascode? Yeah, I mean higher swings. So particularly if I look at the minimum output we can have here, what is the minimum the output can swing to? Overdrive of these two. At the max it's VDD minus 2 overdrive, right? Whereas if you look at the telescopic cascode, yeah, this is the output. What is the minimum it can swing to? It's 3 overdrive. Okay. So with respect to the output swings, it is good. And if you recollect, what is the maximum common mode we can have for the input here? No, but finally if you work out everything, yeah, it can reach as close as VDD, right? I mean, it can be equal to VDD, it can be higher also actually. Similarly, if you use a PMOS input, the common mode can be 0 at the input. So the only reason for you to prefer a folded cascode is to is in scenarios where you are required to drive outputs with very high common modes, or if the common mode at the input is also very high. So only if you are required to have very high swings, you might prefer doing this. Else, as you see, with respect to noise, offset and stuff, this is actually a killer. Great. So that is about folded cascode. So what did we see next? So after this, what did we do? Okay, gain boosting, I'll give it as assignment. And then after that, what did we see? Yeah, we started, I mean, these were the single stage, but then we moved on to multi-stage. So let's do that. This is actually not that difficult. So again, I'll draw it at a block level. So let us say we have a 2-stage, first stage, second stage like this. Okay. And as you know, to compensate this guy, we saw a couple of techniques. One was Miller and feed forward. So for Miller, you added this gap and stuff. But for noise calculations, we'll ignore frequency dependencies because that will complicate calculations. So we'll only look at low frequency noise, right? If you want to have the exact frequency spectrum, you resort to simulator, right? Because you don't get any intuition. So we'll only look at low frequency noise. So we'll ignore all the capacitors. So let's say this is GM1, GM2. Now, as you know, this guy is your 5 transistor OTA. So for the 5 transistor OTA, I already computed the input referred noise voltage for that. We call it like this. So do you recollect what is SVN1 in for a 5 transistor OTA? So I had the input pair and the current mirror like this, right? So I mean, we know these 4 guys will contribute to the input referred noise. What is the contribution due to the input devices? If I write the pass spectral density, what is the voltage noise pass spectral density for a MOSFET? 4 kT gamma by GM. So we have 2 input devices, so that's directly 8 kT, right? Plus, if you find the short circuit noise current due to this guy, what will that be? I mean, if I have a current source here, how much of the current source will flow to the output? Entire current will flow. So that will be the pass spectral density of that current what will be the path spectral density of this noise current? If I call it, let us say M3, M4. Four kT. Fine. So this is the noise output. I mean, this is the path spectral density in the current. You have to refer it back to the input voltage. So what is the transfer function from the input voltage to the current? So what would I do? Divide by GM1 square. Same will happen for the transistor M4 also. So this is, we can see. So basically for any op amps where you feed in the input to a differential pair, this term always comes in, right? 4 kT gamma by GM1 due to one device, you have differential, it's 8 kT gamma by GM1. And then this guy, so you already know this guy. So similarly, what will be the second stage? It's a common source. So if the first stage is an NMOS input, the second stage will be a PMOS input. So again, if I quickly draw that, this is where we apply the input, output. So here again, if I find the, let me label, let's say M5, M6, or yeah, it's fine. Let's say M5, M6, it's okay. Yeah. So if I find the input referred noise for this amplifier alone, can you guess what will that be? So how many devices will contribute to noise here? M5, M6. What can you say about the input referred voltage contribution due to M5? That input voltage directly adds. So its path spectral density is going to come directly. Fine. You are left with finding for M6. For M6, once again, if you do the same business, assume a current, find the short circuit current. The entire current is going to flow to the output. So the path spectral density of that current is what? 4 kT gamma GM6. I have to refer it back to the input. So the transfer function from this current to the input, that's all. So now you know basically how to model the noise for each of these stages. So I can directly write it like this. Okay, Vn2 in. Okay, fine. This is Vn2 in. So now the goal is the following. Let me move to another page. So we want to take this entire two-stage OTA like this. And model the noise with one single voltage source, say Vn in. Okay. So again, for finding the voltage noise, I am shorting the inputs, so but I'll do it. Fine. So I want to model this overall noise generated with one single voltage source. Right. Again, you can do the same old thing. You can find the short circuit current here. Find the path spectral density of the current divided by the transfer function from here to here. But let's try to get it qualitatively, right? So, this Vn in, effective Vn in will have contribution from both these two guys. Fine. So, what will be the contribution of this guy to the input? That's going to add directly. Fine. So, if I write it Vn in, that will contain the first stage. Okay. Any confusions? Okay. So this is sorted. So only the next job is to see how much of this guy will contribute to the input. So again, there are different ways you can look at it. So let us say now I look at, maybe we'll do this. So let's say I look at the voltage here. So let us say what will be the voltage here? If let us say this has a gain of A1 times of Vn1 in. So what will be the voltage here? So Vn1 in. So the question is, I already added Vn1 in at the input. That will give rise to the first term. So what should be the term I should add here? That will give rise to the second term Vn2 in. See, here if I see this voltage, that should be same as this. Fine? Is that okay? Right? So in Vn in I've already included Vn1 in. So Vn1 in times A1 is coming here. I need to add something to this guy so that the second term is also captured. What should that be? Divided by that gain. And basically what I am doing is whatever voltage is here, I am referring it back to the input. So naturally it has to get divided by that gain. That's the other way to, simple way to look at it. Cool. So now if I write the path spectral density, SVN in overall thing, that is Vn1 in of f plus Vn2 in of f by A1 square, right? Okay.
Vn1 in that we calculated when we had output of gain 1.
Correct.
Here we have output at
Doesn't matter, right? So this is basically, this model, see, noise generated by all the transistors here. It doesn't matter where the output is. See, you are saying we calculated by computing the noise here and referring it back to the input. Even if you take the noise here and refer it back, it's going to be same, right? Because whatever noise was appearing here times a scalar factor is what is going to come to the output, isn't it? So finally, if you find the transfer function from here to the final output, that is going to have that additional gain that gets divided. I mean, that is the nice thing about this, right? It doesn't matter where you are taking the output. For anything, for this block, this is the input referred noise. That means that whatever signal I am adding, and if you can think of it like this, along with this input voltage, this hypothetical noise voltage is getting added, and that is what is getting processed by your actual OTA. That's why we are doing this modeling.
the resistance that we are not taking
Which resistance?
in the output of OTA.
Okay, good question, right? See, is this a physical resistor or what kind of resistor is this? It's a R out. So it turns out R out does not contribute any noise. Okay, I mean, that's why, right, in the MOSFET, when we model the noise, probably I should have explained it clearly. The noise is coming, again, if you go to the physics, it is coming because we have random thermal motions in the electrons, right? That is modeled in the current directly. The R0 is our way of modeling this channel length modulation. It's not a physical resistor that is present in the transistor. Okay, so that is why we don't have to worry about it. But if you go ahead and put an explicit resistor here, yeah, then you have to take into account the noise of that resistor. But otherwise, if it's coming from the output resistance of transistors, that doesn't add any noise. Cool. So now this is the deal. So you know, in a multi-stage OTA, maximum gain is coming from which stage? Yeah, first few stages. In a 2 stages, this guy will have the maximum gain. So what can you say? How can I approximate this further? Look at the expression. Can I approximate it further? Only the first term, right? So in a 2-stage OTA, as long as I have a sufficient gain, I don't have to worry about the noise in the last stage. So this notion can be extended further. So let us say I have a 3-stage amplifier. I'll draw it with triangles now for simplicity. Let's say it's a 3-stage amplifier. Again, for each stage, I know what is the input referred noise that you, let us say, calculated already. Say it is Vn1, Vn2 and Vn3. So if I find the overall input referred noise for this cascade, so wherein I'm modeling the noise generated with one single voltage source. Can you tell me what will that be now? Let us say, yeah, okay, Vn1. Can you give me the exact expression first? The first stage noise is going to add directly. Okay. Second stage is getting divided by the gain A1. Third stage noise will get divided by 2 gains. So right. So again you can approximate it as Vn1 as long as you have sufficient gain in the first few stages. I mean, this also makes sense because if I look at the noise from this guy, it gets amplified by 3 gains and appears at the output. This guy is getting amplified by only 2 gains. The last guy is getting amplified by only 1 gain. So overall, this guy getting amplified will be the dominant at the output. Okay. So that is why if we have, if you have a big chain with multiple stages where you have a gain throughout the stage, throughout the chain, the noise contributed by the first stage is the dominant. So this is assuming you have gains in the entire chain. For example, if this is not a gain, if this has a gain of 1, the entire thing goes wrong. Then you can't approximate it like this. Then you have to take into account this. Cool. So that is about 2-stage, multi-stage op-amps. So same goes for offset also, right? So now, even if you try to find the offset, you know that I can model the offset of a differential amplifier using an input referred offset voltage. Let us say VOS in 1, this will be VOS in 2, and so on. So same thing will happen. So the same framework we have for noise will hold good for offset also. So even if you find the overall input referred offset, if you write it exactly, it's going to be offset, input referred offset of the first stage plus the input referred offset of the second stage by the gain, input referred offset of the third stage by 2 gains. So if you find the sigma square of this, you can approximate it as sigma square VOS. Right? Cool. So after multi-stage, what did we look in the course? This compensation is what is multi-stage, right? Feedforward is also multi-stage compensation, right? You can work out the same way. Fully differential op-amps, right? So let's look at what happens there. So again, I'll give a top level understanding because again it is very simple. So if you think about it, all your fully differential amplifiers, so you can think of it like this: we have 2 identical half circuits. So you give let us say inputs here and tap the outputs here, right? Of course, if I just ground it and take it, is it a fully differential amplifier? No, it's a pseudo differential. It lacks, what does it lack? Oops. Yeah, the common mode rejection is not there. So essentially, along with that, you also have something here. I'll call it common something that gives a rejection. Typically, it's a current source, right? And this common network can also include your CMFB, right? So CMFB is also going to sense the output and do something. That will also add in the common mode. So now let's look at the noise contributed here. So as usual, as long as you are applying the inputs to the gates, we require only a voltage noise to model this. And to find the voltage noise, what do I do to the inputs? I'll short the inputs, that is RS is 0. And then I'll find the same thing. So now let's divide it into 2 parts. One, let's try to find what happens due to the noise in this common network, and then what happens due to the noises here, right? So if you look at the noise in the common network, so let us say something here is injecting some noise current here, right? And let us say now I look at the differential output. So what do you think will happen to this? So remember, these are identical networks. So this noise current is going to get equally divided. So it's going to get processed by the same network in the same fashion. As long as you are taking the output difference, it doesn't come, right? So any noise coming due to this common network, that doesn't add to your output. This will also include part of your CMFB because that will also be adding in the common. But in CMRP, you should be careful. The common mode sensing resistors might contribute to noise. So you should just be careful. So anything that loads your differential thing, you should be careful. That's all. So this is okay. So now let's look at the noise generated by the network here. So remember that these are two identical networks, two half circuits, right? So let us say I take one transistor in this network, say it has a voltage noise VNK. I'll call it VNK plus because it is in the positive side of the network. So I'll have an identical transistor here that will also generate a noise. I'll call it VNK, kth MOSFET in the minus side. So both transistors will be identical, so they'll have the same GM, say some GMK. If that is the case, what can you say about SVNK plus? That is the input, that is the voltage path spectral density of that MOSFET. What will that be? 4 kT gamma by GMK, right? So even in the other side, the transistor has the same GM, so that will also have the same path spectral density. Okay. But one thing to notice, these two transistors are independent, that is, they are two separate transistors. So what can you say about the noise in the two transistors? They'll be different. Can you be more mathematically correct? They'll be uncorrelated. Okay. These are two different transistors. The noise is getting generated by different mechanisms in the two transistors. So the noise will be uncorrelated, but the path spectral density will be same, right? So let me mark it here, VNK plus, VNK minus. They are uncorrelated. Cool. So now let's try to find what will happen due to the, let's try to find the output voltage here differentially. I can also find the short circuit current, but here let's try to find the open circuit voltage. So let me copy this. So now I have a differential circuit like this, fully differential circuit. I have two different inputs. I'm interested to find the output. How do you think I can go about solving this? Okay, yeah, superposition can be used for any linear network. But here, besides linearity, this is also a symmetric network. So what do? You decompose them as common mode and differential portions. So let me, basically that means VNK plus, I can write it like the common mode plus half the differential. Similarly, the negative is this minus this, right? So now I can basically replace, I can assume that I'm exciting the network with first the common mode. Okay, I'll call this as different color. I'll call it VNKC. Okay. So here the here the voltage that I'll consider will be a common mode thing. VNKC. Here also it is. So what will be the differential output? 0, right? Again, it's a common circuit. It is the same identical network. So the voltages at both these points will be same. Differentially 0. So this is not contributing to any noise, right? So rewrite it. So then we have to find the noise due to the differential portion. So now let me take which color? Maybe let's say this color. What color? Okay, yeah. This is, let us say, VNK differential by 2, right? So here I'll replace it with differential excitation. So it's here it is plus VNKD by 2. Here it will be negative of that. Okay. So now how can you solve this now? To simplify this, can you do something here? it's a differential excitation. Is there something that can be done now? Yeah, the common, again, once again, all the nodes along the line of symmetry, they will be 0. So this guy is not playing any role. So basically now this is split into two half circuits nicely. Right? So now rest of the calculation I'll just give it, and I'll just hand wave and then make you work in the assignment. So here now this is one half circuit. So here for this guy, just like the kth noise source V and K, I'll have lots of noise sources. I can replace every noise source by a differential noise like this, right? And then find an effective input referred noise voltage for this guy. So if I find that, let us say I'll find Vn plus, that is the input referred noise voltage for the positive side half circuit. So that will be basically some Vn k d by 2 times some gain alpha k divided by some gain, right? Some ak, something, right? Okay, this is what you'll do. So basically I'm finding how much of this appears to the output. I'm assuming that gain is some alpha k, and then you refer it back to the input, and that gain I'm assuming to be some a, something, right? So we'll find this. So similarly, if I find the input referred noise for the other half circuit, what do you think that will be? Same or what? It will be minus of that, right? So that will be Vn minus in, that will be negative of Vn plus in. So now I am not interested to find the input referred noise of the half circuit, but for the overall differential thing. So I need to take the difference between these two, right? Is that okay? This is only for the half circuit. Again, similarly for the other half circuit, it is something. I am finally interested in the differential picture where I am interested in the difference between the two signals. So I'll basically take the difference. So it's going to become twice of this, right? So the result I'll say from here you can basically prove it. So what will happen is this. The end result turns out to be the following. So you take one half circuit. Okay. So what you do in the half circuit is the following. In this half circuit, you just take V and K as it is, not the differential, just the noise voltage for each element as it is. You find some input referred noise for this, right? You multiply, input referred noise of this, and let us say that is some Vn in of f. You multiply that by 2, that will give me the, let us say, still. Okay. From here I want you to prove it, right? Till this point I hope it is fine. So you take the difference, you will get twice of this, and then you take the part spectral density and use the fact that the noise sources are uncorrelated. You will have Vn kd by 2, replace it with Vn k plus minus Vn k minus by 2, and then take the part spectral density. So finally what you will find is, you will the input referred part spectral density for the fully differential circuit is twice the input referred part spectral density of your differential half circuit. That's all. So what that means is, I will just give an example so that you understand it. So let us say, let's take a simple diff amp, fully differential case with this. Okay. So here if you want to find, let's say this is the output. So here to find the input referred voltage noise PSD for this overall differential amplifier, you construct the differential half circuit. Just this, right? For this you try to find what is the input referred noise PSD. Can you tell me what will be that? Let us say this is RD, let us say this is M1, let's say SVN of F. Yeah, what is it? The transistor's noise is going to directly come, there should be no confusion. Similarly, now let us say you find the short circuit noise current from the noise current of RD to the output. That is directly going to come. So part spectral density of that noise current is what? 4 kT by RD divided by, this is the part spectral density for the differential half circuit. You basically multiply this by 2. That is the part spectral density of the fully differential amplifier. That's all. So I'll give it as an assignment, you work it out. So from this point, you prove that this is the case. Right? So yeah. So yeah, that's all. So I don't have to do any examples because now you know how to find the noise for each half circuit. You just multiply it by 2, we'll get it. Great. So yeah, if you followed till this point, anytime you should be asking some question. So since you are not asking, I'll ask it myself. So it looks like for the fully differential case, the noise PSD seems to be 2 times the noise PSD for a single-ended case. So the natural question is it more noisy actually? Is it worse than a single-ended circuit? Because for fully differential circuits, we saw a lot of advantages with respect to common mode rejection. But looks like with respect to the input referred noise part spectral density, it is 2 times bad. So the natural question is it the case? And it turns out that's not the full story, because in practice we are not only interested in the noise power. What we are interested in is in the following. So let me take this case. So let us say I take one single-ended half circuit wherein it takes only one input, one output. It operates with a supply, say VDD and 0, right? And let us say it has some part spectral density SV of F, right? So now I take 2 copies of this, add common mode rejection, make a fully differential circuit. This is the composite network. So this will also be running the same supply. So here if I find the part spectral density, it is going to be 2 times the old one, right? So essentially from the part spectral density, if I were to find the noise power, what do I do? If I know the part spectral density, to find the noise power, I'll integrate the part spectral density from 0 to infinity, right? Please remember, part spectral density gives noise around one frequency in a 1 Hz bandwidth. The total power is present in all the frequencies. So we sum up all the terms. So here let us say you integrate it, you get some sigma square n. So here what will you get? Here if I do this, I'll get, right? But in practice we are not only interested in noise power, we are interested in something called signal to noise ratio, right? We want to see how much is the maximum signal power the system can process and how much this maximum signal power is higher than the noise power, right? So here if I try to find that, so first of all let's see, here the swings are from, the supply rail is from 0 to VDD. So what is the maximum sinusoidal input I can apply here? So it has to be centered around half. What is amplitude, maximum amplitude? Not VDD, VDD by 2, right? So what is the maximum signal power? Yeah, if I do this, it's VDD square by 8, right? Okay, VDD by 2 square by 2, fine. So if I find the maximum signal to noise ratio, what is that? Right. So let's try to do the same thing here. So here I don't have one input, I have 2 inputs, right? So for each of the inputs, I have the same range, 0 to VDD. So it has to swing again around half the thing. If one of them does this, the other one will do the opposite. So now can you tell me what is the maximum differential sinusoidal amplitude I can apply? So here it's VDD by 2. In the negative it is minus VDD by 2. Differentially VDD, right? So maximum signal power is So if I find the maximum signal to noise ratio, it's VDD square, right? So now it looks like the maximum signal to noise ratio you can get from this fully differential circuit is how many times higher? 2 times higher than what you can get with a single-ended circuit. So which means you should ask the following question again. So is it better? I mean, are we gaining, it looks like it is better, so is it coming for free? So what is the price we are paying? Yeah, but finally I'm not interested in noise, right? Signal to noise ratio, if I look at it, it is kind of higher. But okay, but what can you say about the power consumption? Here I have 2 times the same circuit. Power consumption is increased by a factor of 2. Signal to noise ratio is increased by a factor of 2. So that's the basic trade-off. So in fact, this is a fundamental trade-off between power and noise. Okay. So that brings us to the next part. So now, you guys know how to analyze the noise, find input referred noise current, noise voltage, power spectral density, and so on. That is nice to calculate and estimate. And you can also design your circuit to meet the particular noise, right? Let us say you are given, in your op-amp design, I didn't give it, but maybe I'll add it now for the second project. Let us say you are given a spec that the input referred noise PSD should be something. That will set a limit on your GM1, right? Because as you know, this is going to be some 8 kT gamma by GM1 plus something. So you should design your GM1 based on this. So as a designer, that's what you will do, right? You analyze nice, but the reason we are analyzing it is you should be able to use the result for your design. So this is nice, you can do. But let us say now we have designed this. But later, let us say let us say in your company, your manager says, no, I want 2 times lower noise. Same specifications, nothing should change. My gain, UGB, phase margin, nothing should change. But I want 2 times lower noise power, right? So you should also be knowing how to do that. So I'll just briefly explain that. So basically from here you already saw, right, with respect to the, there is a fundamental trade-off between noise and power, right? So if you want to reduce noise, can you suggest a simple way in which this can be done? Somehow you have to increase power, okay? That's what will happen, and we can see that with a simple example. Again, I will not prove it very formally, I'll just give an example to make the point clear. Let us say you take a simple transistor, common source, right? What is the intrinsic gain of this guy? Let's say magnitude, if I look at it, it is GMR0. Okay. Now, let us say that, yeah. Okay. Now let us say that, here what is the input referred noise PSD? 4 kT, right? Only the transistor is there, it's fine. Now the goal is I want to reduce this noise power spectral density by a factor of 2. So from here, what is the solution? What should I do? I have to double the GM. Again, the way to double the GM without affecting the operating point voltages is what? It's like you put 2 transistors in parallel, right? We have already saw this during characterization things. If you put 2 of them in parallel like this, GM doubles, and total power also. What can you say about the current if this is I0? The total drain current is 2 times A. Okay. So this way you can do this, and now if I do this, what can you say about the output resistance? Sorry, not output resistance, the intrinsic gain. I had 1 transistor earlier that had a gain of GMR0. Now I seem to have put 2 of them in parallel. What can you say about the gain? So GM has become how much? Now what happens to the effective output resistance? So gain is, so this is one way. So although I have shown it for 1 transistor, you can just extend it. So the idea is the following. Let us say you have designed some circuit. let us say you feed the input here, take the output here, and it has lot of internal nodes in the circuit. So it has some transfer function h of s. Now the goal is I don't want to modify the transfer function, but just reduce the noise power spectral density by a factor of 2. For that, what you do is the following: you take an identical copy of the same network, and then just connect and then connect all nodes one by one like this. Okay. That is basically putting every element in parallel. So if I do that, see, these are identical circuits. So if I apply some signal here, the node voltage here and here are going to be same. So even if I go and connect it, nothing is going to change. That's how we are making sure that the transfer function also doesn't change. Right? So if I do this, if I have a resistor R in the original network, after putting two of the networks in parallel, what will happen to the effective R? R by 2. If I have an inductor connected somewhere, if I have a capacitor, 2C, and if I have a OTA, some GM. Okay. So now you should get the idea. So if you have some network, let us say it has all these guys, right? So if you want to make sure that you don't change the transfer function and just want to reduce the noise, let us say by a factor k. So which means, what should I do to the resistors in the network? All resistors in the network should be scaled by factor k. Inductors should become L by k. Capacitors should become k times C. GM should become k times G. If I do this, the path spectral density will reduce by a factor of k. But what can you say about the power? Power will increase by a factor of k, because you can think of it as putting k of these networks in parallel. If one network is consuming a power some p, k of them will consume k times p. So this is called impedance scaling. The idea is you essentially scale all the impedances by an appropriate factor to get desired noise. So again, you can also go the other way, right? So let us say you design the circuit, you find that the noise is very low. Let us say you're okay, and basically you find that the noise is very low. Yeah, and then power is high. You want to reduce the power. Simple thing is, you do the reverse way. You take each resistor and increase it. Inductors, you increase it by 2 times L or some K. I'll make it generic. So let us say M times R, M times L. C will become C by M. So if I do this now, what will happen is power will reduce, but noise will increase. And basically, if you want to reduce the GM, what you do is this: you put multiple transistors in parallel. Okay, great. Yeah, so generally what you will find is, see, now let us say you want to characterize your op amp, right, or some analog circuit. Let us say you want to characterize with respect to noise and power, right? Now it looks like if I only look at the noise, that is not a great metric, because I can reduce the noise. Brute force way to reduce noise is to basically increase the power. Similarly, if I look at only the power, it looks like I can arbitrarily reduce the power by by having higher noise. So what would be a metric to look at? Yeah, power times noise. Right? This is the metric you should be looking at. If this metric is lower for your circuit, the circuit is better. Right? Again, this is, typically this is one of the figure of merits for an analog circuit, and this is a fundamental thing. Cool. So maybe some few minutes, let's do this. Yeah, you guys free for 5 minutes? Okay. So let me copy if I have the file transfer OTA. Let's do a simple exercise, not an exercise. Let's see how you. Okay. Okay, just a second, this guy is misbehaving. Yeah, okay, let's say do this. So what I wanted to do is the following. See, now you know the circuit, right? How to design this, you know, right? And as I mentioned in the beginning of the course, the number of transistors you find in an analog circuit is orders of magnitude smaller than what you'll have in a digital circuit, right? So if you're always doing it by calculations, basically if you're only relying on quantitative calculations, that is not great, because a computer will do a better job than you. So why you get paid for is the way you intuit the circuit, right? The number of transistors is small, but you should know what each transistor is doing and what will change if I change something in each transistor. So let's see if we can do that. So let me draw the biasing also. Right, so let us say something. Okay. So let's start with this guy, right? So let us say increase the width of M0, or not M0 alone. Let us say I increase the, say this I0. Let us say this is M minus 1. Okay. M minus 1, M0, both widths are doubled. So what will happen now? Or let's say not double, some increase. Let us say what all will change? Why will current through M0 change? Both their widths are doubled. I0 is not going to change, right? So with respect to the DC operating point, nothing will change here, right? I0 is same. So if I, for the same current I0, if I increase the width of this guy, what will happen? The current is same, I am increasing the width. Huh? Not necessary, right? I mean, why should I'm just, this is, I'm not changing anything. Let us say I changed it. Now what will happen? What will happen to the overdrive? See, for the same current, if the width is higher, the gate to source voltage will what will happen? See, the current is same, width is increasing. What should happen to the second term? That should decrease. So overdrive reduces, so this guy goes, right? So if this goes, what all will change? See, think of it like this. When I change something, look at what happens to the operating point picture and what happens to the small signal parameters. So with respect to operating point, gate to source voltage reduces. So is it good or bad for this transistor? Why? Why will this go out of saturation? Okay. If it goes well below threshold, yes, that is one thing. But if not, it is fine. In fact, the drain voltage is fixed. The gate reduces, this is nicely in saturation. But like you pointed out, if you reduce this further and further, this can go into what is called weak inversion. We'll discuss it late in the next few weeks. That is one thing. And also, if I increase the size of it, what else will change? Let's say operating point you did it. What else will change here? If I have a larger transistor, capacitance is going to be higher. So let us say the gate capacitor is higher, and let us say even the drain also, the capacitor slightly increases. So if this cap increases, is it good or bad? Why bad? Why good? Capacitance affects the gain, but does this capacitor impact the gain? That's the question. Yeah, okay.
Current and voltage we should take it account.
While modeling noise,
If it is not there,
uh-huh.
then directly with voltage source alone.
Okay, that is true. But let us say, I mean, we can model. Yeah, that is true. What he's saying is, yeah, I mean, for a transistor, the noise model that we have only a equivalent voltage noise at the gate is valid only if the gate capacitance is not there. Yeah, that is fine. But we can still calculate the noise using current source here, right? This is the ultimate model. So let's say with respect to noise, what will happen? If I didn't have the capacitor, the noise current is injected here. What will be the voltage here? Small signal voltage. If the noise current is IN by GM. Now if the capacitance is there, what will happen? Let us say you find it versus frequency. Yeah, you'll find that it is going to be IN of S. So if the capacitance is large, what will happen is, I mean, at high frequencies, the noise voltage here is going to drop. Is it good or bad? Good, right? I mean, see, simply speaking, what is the point of this gate voltage here? I mean, what is this gate doing here? Or, I mean, yeah, it is only there for biasing this at a particular current. So as long as this voltage is fixed, we are okay. If I go and put a large capacitor there, that capacitor is going to get charged to the required voltage. That is going to act like a, loosely speaking, a battery there, right? For any DC point, you put a large capacitor, it's actually good. So this cap is okay, might not impact you so much. But let us say this cap increases. What can go wrong? Sorry? Why? Yeah. See, remember that earlier, let's say this guy was open or small signals. If this was open at small signals, if I draw the common mode half circuit, I'll have, I mean, for common mode, both these guys are same. I'll short it. You'll have a diode connected something here. This will be open. Now if I apply any common mode signal here, there is no path for the incremental current to flow. Common mode response is 0. But now if I have a capacitor there, at high frequencies the capacitor will indeed provide a path. So the op amp will start to respond to common mode signals. So if we have a large capacitor at the tail node, so this guy will impact your high frequency common mode response. I'll say CMR. Right? So let's do one more thing. So let us say now I increase the let us say only increase the current here. Okay. So what will happen? Let us say let's see what will happen to the actual circuit. I mean, basically I have increased the DC bias current here. So what all will change? With respect to the operating point, what will change? This is, let me mark it maybe. The overdrive will increase or decrease? Current is increasing. Okay, overdrive will, yeah, okay, increase, sorry, correct, yeah. If overdrive increases, what can you say about this voltage? That will decrease. VGS is increasing to keep the same current. So this guy is reducing. So if VS reduces, what can go wrong? So that's something problematic. So what will happen to the incremental gain? So current becomes 2 times, right? Everything else is same. What will happen to GM? Right? So here only the current changes, these two guys don't change. So GM becomes, what will happen to R0? Current is increasing by a factor of 2. R0 will become, so what will happen to the intrinsic gain? It will reduce by factor of root 2. 1 by root 2, right? Yeah.
GM we go with that relation 2ID by VGS.
You can do that, right? 2ID by VGS minus VT. So now you tell me, here the current has changed. Current has become 2x. But what can you say about this guy? That has also changed. So that also you take into account, then you will get that.
Overdrive is also increasing.
Yeah. I mean, you find the exact thing, right? I mean, I know that current is proportional to overdrive square. If current is becoming 2x, overdrive should become, so this becomes 2x. I mean, you can use any relation, just be careful, right? You should make sure that should take into account what happens to each parameter in your expression. That's all. Okay. So I think I'll stop here. You can give some more as an exercise. You can work out. But this is what